Okay. Give me a moment. Okay, let's get started. So today we'll just go more to ideals, just so you are all more familiar with it. And that's the best thing to do. So we'll be doing more questions and whatnot. So okay, but let's go over like prime fields. So think of these as like base fields, yeah? So if I have a ring R, right, with unity, I always have a map from Z to R, right? Given one goes to one. And this determines the whole map, right? Because any other integer, like n, is just 1 plus 1 plus 1 n times, right? So question, what is the kernel? Can anyone tell me? The kernel, so in other words, here I'm sending like n to n, you know? So what's the kernel? It's what you're gonna notice is, if you remember, what is the characteristic? It's the smallest number such that 1 plus 1 plus 1 that many times is 0, right? What you notice is that that's the kernel, right? Because the characteristic of R equals n, that means, you know, n times gives 0, right? So this is an R, right? And that's what you notice is this is precisely what the kernel is, right? It's pretty much nz, right? If, you know, and like if it's 0, then 0z, we just treat it as 0, right? So you see here, right, by first isomorphism theorem, isomorphism, or I think the book calls it what, like fundamental homomorphism theorem. Theorem, right? Z quotient kernel, which is nz, is isomorphic to image of phi, right? So again, we don't know it's surjective, so but we do know it's surjective to the image, yeah. So it's whatever the image is. So, and we know the image is a subring of R, yeah? So, there are two cases, right? When n equals 0, this is just Z, right? Where isomorphic is Z. When n is bigger than 0, your ring has a copy, sort of like has a copy of Z mod NZ or Z. So that's the first thing, right? So this is a corollary, right? If R is a ring with unity, and characteristic of R is bigger than 1, let's call it n, then R contains a subring. So the subring is image of phi, yeah? So subring isomorphic to Z mod NZ. So you should think of it as you have a copy of Z mod NZ in your ring. And if R, and if n is, if the characteristic is 0, R contains subring isomorphic to Z, right? Yes, so you sort of see like if your characteristic 0, like the smallest ring you can have is Z. And it sort of makes sense, right? Because if you have a ring of unity, you have 1. And you must be closed under addition, so you must have all multiples of 1. And then you must have inverse, so you must have all negatives. So you see Z is like the smallest possible ring, right? And like every other ring contains 1, with characteristic 0, you must contain a copy of Z. So everyone follow? Yes? No? Does this make sense? Okay. So in particular, if R is a field, right, then either you are characteristic P, or contain subfield isomorphic to Q. Yeah. So again, use the corollary above, right? So if I am characteristic of R is n, suppose is 0, then I contain Z, right? But there's many ways to argue this, but R is a field, right? We're assuming it's a field, and Q was the quotient field, right? It's the smallest field containing Z. So since R is a field and Q is the smallest field containing Z, and R contains Z, R must contain Q, yeah? Or it's either equal to Q or it must contain Q. So then, what is this? Not I. R contains Z. So, that's one way to argue it. Another way is you can just argue by field property, right? If R contains Z, right? So Z is a subset of R, right? Well, R is a field, so every element in R, in particular, every element here, because you contain a copy of Z, you must have all the inverses, right? And once you have all the inverses, if you have n, you must have 1 over n. Well, R is a field, so you must be closed under addition. And then, so you see you get 2 over n. So basically, with addition and inverses, you get P over Q for any PQ. Yeah, so you see you must contain the rational numbers. Okay, and then obviously, if characteristic of R equals n is bigger than 1, then what? Well, then from the corollary, we contain a copy of Z mod NZ, right? But N must be P then, as if not, Z mod NZ has 0 divisors, right? If you're a composite, then you have 0 divisors. But R is a field, right? And a field cannot have 0 divisors. So you see fields are either characteristic P for P prime. We're gonna write P prime, or they're characteristic 0 in which they have a copy of Q, right? So if you think of any field that's characteristic 0, like R, C, right? They all contain a copy of Q. Yeah. So we think of like Q and Z mod PZ as like prime fields. Yeah, they are like the base field. Yeah, they're one of them is if you have a field, your field must contain like a copy isomorphic to like either this or this. Okay. Everyone clear? Yes. Okay. So moving on. Principal ideals. So I wrote this a lot. Principal ideals. So your book writes it like this. Some other books also write it like this. Yeah. So I'll just write comma, like it depends on the book. But this is the set of RA such that R is an R. Yeah. So from here, right, so this is given ring R. And A is an R. Yeah. This is like the principal ideal. So think of it like if I gave you a group, right? If I gave you a group G, it's kind of like the subgroup generated by your element. Yeah. So like think of it like, subgroup generated by A. We also write it like this, right? If you remember, so for example, Z mod NZ, like the subgroup generated by like 2. Let's do something like a clear example like 6Z. Yeah, the subgroup generated by 2 is 0, 2, 4. Yeah, it's all the things you could get from powers of 2. Yeah, so it's sort of the same idea here. We're sort of generalizing it, right? So here it's all the things you can multiply R2 by A. You can multiply A by 2R. So we're sort of generalizing like subgroups generated by elements. So this is like for rings. Okay, so here's a fact, right? Every ideal in R, every ideal in Z in the integers is generated by N for some N in Z, right? So, from their notation, it's like this, but some of you probably know the notation as NZ. Yeah. So these are like the same thing, right? Because if you think about it, this is what? Like, this is the set of Z times N such that Z is in Z, right? Because, we're commutative here. So let me just say, given commutative ring. Yeah, so if it's not commutative, then these you you might have to differentiate between left and right. Yeah, so there's like a left ideal, right ideal. But for our purposes, let's just go with commutative for now. Does everyone remember why this is the case? Do you need me to go over that? Like, can you prove to me every ideal is generated by like one element? Yes or no? This is something you should know. So, do you need me to go over this? Yes? No? So, like, if I ask you, can you prove to me every ideal in Z is generated by? No. So, I mean, so my question is, if I say given I ideal in Z, my question is, show I equals NZ for some N. Can you like at least explain to me why that's true? Like even without like a proof. I mean, so like, how about this? I'll let you write out the thing, you know, the whole thing. But suppose it's generated by more than one element, right? Then the idea is you can reduce it. So this thing, I claim, if it's generated by two elements, this is generated by GCD of XY, parenthesis. So so how do you show two ideals are equal? So this is like the ideal generated by, it's this notation. And then this is just the same for like two elements. But for here, right, the idea is like, okay, what does GCD mean? GCD divides this, right? So X is GCD of XY times K, right? For some integer K. Y is GCD times XY for some integer L. Yeah. So from being a divisor, right? We get that X is in here, right? And Y is in here, right? Because I mean, this thing is the set of K times, I'll use a different ring, Z times GCD of XY, such that Z is in Z, right? And I just wrote X and Y of that form. Everyone agree? So since X and Y belong here, well, certainly GCD of XY, this thing contains this thing, right? Because if I could write if X and Y belong here, then the ideal generated by X and Y belong here. And then for the other way, it's using the Euclidean algorithm. Euclidean algorithm. So if you remember, by definition of GCD, there exists Mn such that Mx plus Ny is GCD of XY, right? That's the nice property of the greatest common divisor. And then you're done, right? Because so this thing, right? This thing is in XY. This thing is in XY, right? I mean, this thing, because the element mx, you could write it as mx plus 0y. And then this thing is 0x plus ny, right? So it's certainly in the ideal generated by x and y, but the ideal is a subgroup, so that means this whole thing is in xy, but the whole thing is equal to this, so this is in xy. So this shows that xy, since xy contains this thing, right? It certainly, contains the ideal generated by xy. And then you're done. Yeah. So the idea is, if you have more than one generator, you can just keep reducing it to like, smaller and smaller. That's the idea. Everyone clear? Yes. So what I'm saying is my n in this case. So if this was my ideal, my n is GCD of xy. Yeah. Okay. Moving on. So if F is a field, every ideal in f of x, so I think your professor will prove this, but every ideal in f of x is principal. Yeah. So every ideal in your field is in, obviously the ideals in the field is just zero in itself, but we're talking about the polynomial ring now, and we're saying everything here is principal. Yeah, it's generated by one thing. So note that this is not true if f not a field, right? One thing you could, for example, take r to equal z and consider z of x, right? So z is not a field. So I claim this is not there are non-principal ideals. Yeah, so the one I'm gonna tell you is considered the one generated by 2 and x. Yeah, so if this was generated by one element, let's call it f of x, right? So if these were equal, then 2 must be in here, right? So 2 must be in the set of, g of x times f of x, such that g of x is in c of x. So 2 is equal to some g, let's call it g1 of x times f of x. But if you argue, right, z is an integral domain. So if you argue by degree, right, this forces this degree of g1 of x to be 0, degree of f of x to be 0, right? So f must be a constant right here. Yeah. Now you argue, well, x must be in here, right? So x, the ideal generator x must be in the ideal generated by f of x, but f of x is a constant, so let's call it like n. Yeah, where n is not equal to 1 or -1. Yeah, so n cannot be 1 or -1 by a simple argument, because in which case you have the whole ring, right? And 1 is not in here. So then you're almost done, right? I must find a g, so x is equal to g2 of x times n. But so by degree argument, g2 must be linear, right? It must be degree 1. So this is like ax plus b, yeah, times n. And you see it's impossible, because from here, you're basically saying anx plus bn, right? So you're basically saying an is 1, right? If you match the coefficients. And of course, bn is 0. But this is impossible, right? Because if n is not 1 or -1, this is impossible because the only units in z are 1 and -1. So you can't find such a G2. Yeah. Is everyone clear on this? So if this was a field, right? If R was like, I don't know, Q, and you consider Q of X, right? The ideal generated by 2 and x, this is principal. It's generated by 1. It's the whole ring. Yeah. Because again, once you have 2, right? Like 2 is in here. So in particular, if I multiply by a half, right, I'm still in here, right, by the magnet property of the ideal. And you know that once 1 is in your ring, you basically get the whole ring. So yeah, it's principal. Is everyone clear on this so far? Mostly. uh, yeah, so another way to think of this is, how about this? Z and the ideals in Z and Q, you're not, Q is sort of like, you should think of it as, you're not, it doesn't really have ideals, right? There's 0, and then there's just the whole ring, right? So when I adjoin X, right, I I can have like, 0 and like a variable, right? But 0, that doesn't change anything. So it's just the variable, right? And like and the idea generated by Q, well, that's just 1. And once you have 1, you have the whole space. But Z is different. Z, you have 0, N, and like the whole ring, right? So like it's possible to have like NX, sort of like the one I do here. It's possible to have like a non-principal one. That's sort of the idea. Like your Z sort of has like too many ideals. So now when you adjoin X, you could take one of those ideals, like the non-trivial ones, and then just adjoin it with like X or something to get like an extra dimension in a way. Uh, okay. Moving on. So let's do some questions and then we will call it a day. So we'll do a lot of questions today. So suppose F is a field and characteristic of F is 2. Yeah. Can the order of F be, I'm just going to make it up. I don't know. 1, 5, 5, 5. Anyone? How about like yes or no without a reason? Can you just say yes or no? Uh, so later on, you'll realize that all fields have prime powers, the order, but for now, you don't need that. All you need is, what does characteristic of 2 mean? Can anyone tell me what does that mean? It means 1 plus, it's the smallest integer, right? So that means 1 plus 1 is 0, right? Does everyone agree? And this is the smallest such thing. Okay, but what do we know about addition? A ring is what under addition? use the definition of a ring. In particular, it's a group, right? So what does 1 plus 1 equals 0 mean? It means what's the order of 1? Yeah. So think of characteristic. Characteristic is pretty much just the order of 1, right? It's the smallest n such that, when you add 1, that n times is 0. But 0 is the identity, is the additive identity, right? So can it be possible? Can you use group theory? What does Lagrange say? If order of f was 1555, what does Lagrange theorem say? Yeah. So 2 divides this, but that's not possible, right? So no. Later on, you will see that all finite fields have prime power order, but for now, just no. This is just group theory. So I'm basically saying if it's characteristic 2, it can't be 10 either, right? It has to be a power of 2, but you will learn that later. So let's move on. Example. Find maximal ideal. Let's practice, yeah? Maximal ideal of Z cross Z. So before I continue, can anyone tell me, like, if I have ideal I of Z, J of Z, right? So these are ideals. Can anyone tell me what this is? So you can check that this is still an ideal because I and J are ideals and all operations are just component wise, right? If everything is done component wise, well, if all you need is for each component to be an ideal, right? And if you think about it, really, if you think about it, that this this is pretty much, right, like the same as like this, right? Because I mean, like, everything is done component wise, right? So like when you add like AB with like CD, right? This is like A plus C, B plus D, right? So like one component has like no effect on the other in a sense, right? I mean, if addition was weird, right? If it was like, I don't know, AC plus BD, if it involved like both, if one component involved like both components, but then yeah, it's not obvious. But since everything is just component wise, you could pretty much argue this. So knowing this, can you give me a maximal ideal? Can you find me some I and J such that this works? Is done component wise. Okay, how about this? Why am I telling you to use quotients? So if my ideal was maximal, what do you know by when you quotient? Like what is that ring? If I have a ring R, yeah, it's a field. Okay, so I'm basically asking you, give me an I Give me a J such that this is a field. No, Z2, no. So if I was 2Z and J was 2Z, then Z cross Z quotient 2Z cross 2Z would be Z cross 2Z times Z cross 2Z. This thing is not a field because it has zero divisors, right? 0, 1 times 1, 0 is 0, 0. Yeah. No. So same exact argument. 0, 1 times 1, 0 is 0, 0. There are zero divisors. So you need to get rid of one. So you know Z cross Z mod 2Z is a field, right? Z mod 3Z is also a field, like alone. So how do you make it alone? So I'm saying get rid of one of the components. So how do I get rid of one of the components? How do I just take, how do I get rid of this Z? What should I choose J to be? Yeah, you just mod out by Z, right? So, so take this will work. Yeah. Because this is then isomorphic to Z cross Z, Z quotient, but Z quotient Z is just 0. Yeah, if you think about it. So yeah, because the class of 0 is everything in there. So is this clear for everyone? Yes, no. Okay. So now let's continue. I'm going to keep it the same page. Prime, but not maximal. So the third one you gave already. I was going to ask not prime. So not prime, like this works. Yeah. So what about prime but not maximal? So what do you know about when you quotient by a prime? What must your ring be? Integral domain. So basically what you want is you want to quotient it out, right? So, but not maximal, right? So you want it when you quotient it to not be a field, but you still want an integral domain. Yeah. So this thing, certainly when you quotient, it's not a field, but it's also not an integral domain. I told you, right? There was zero divisors, right? 0 times 0, 1 times 1, 0 is 0, 0. Wait, how about this? Can we all agree that we must get rid of one of the components? Because if we have if we have both components, the 0, 1 times 1, 0, that will always be a problem, right? So one of it, we have to get rid of one of the components, right? So let's take J to be Z. Yeah. So all that's left is to find what I is. So I'm asking you, Z quotient what gives an integral domain? I guess integral domain, but non-field. Yeah, you want to just be left with Z. Remember, all ideals of Z are of the form NZ, right? I just proved that last slide, right? With like the GCD thing. So, or half proved, I guess. But, right, so you know the ideals are NZ. So the quotient is Z mod NZ. Well, you don't have much choice, right? Because if N is prime, it's a field. So that's out of the question. If N is composite, you have zero divisors, right? Z mod, like Z mod 4Z has zero divisors. That's also out of the question. So really, no, Z mod 1Z is just Z mod Z. That's just zero. um, I mean, I guess is the zero ring prime? Let me think. Uh, how, how do they define is the no, it's not because don't they define integral domain as like a commutative ring with unity where one is not zero? Um, Zero is not maximal. So like if I take I to be zero, then Z quotient Z mod out by zero quotient Z is Z quotient zero cross Z mod Z, which is this is Z cross zero, right? Which is Z, right? It's not maximal. This is not maximal because if it was maximal, Z would be a field. Yeah. So, but Z is certainly an integral domain. So yeah, that works. Uh, is everyone clear on this? Yes, no, kind of. Is there some part you're confused about? Uh, don't work. I'm saying so. I mean, so if you get that, then your only choice is zero or Z, right? For I, yeah. This is. I'm saying Z might. I mean, Z will work. I just forgot what the definition of integral domain. Like integral domain, if you choose Z, then this is just the zero ring. Yeah. So if they define integral domain as commutative ring, um, with what do you call it? No zero divisors, commutative ring with unity, right? And if they say with unity where one is not zero, then then yes, yeah, then yeah, then I equals Z will also work. I just remember sometimes they include the part where like one is not zero. So if they add that part, then this will not work. Yeah. Right. So let's move on. Okay. So I'm gonna give you a motive before we do this question. I'm gonna give you a motivation. IB ideals of R ideals. Ugh, that looks so weird. Okay. Ideals of R, and we're gonna consider this set. Yeah, the product ideal. Now sum I equals 1 to n ai bi, where ai is in A, bi is in B. Yeah, and n is in like it's just some positive integer. Yeah, so before we, before the question is, A, prove AB is ideal. And B, prove AB is a subset of A intersect B. This part B is easy, but I know some of you will start asking, like, why do we not define it as this? Can anyone tell me why? There's a reason for this. So my question is, if you try to prove this isn't ideal, what fails? So why not? Anyone? So what about closure under addition, right? If I had AIBI plus AJBJ, you would have to guarantee me this is AKBK, right? For, where AI, AJ, AK, and A. But you see that this is like, not necessarily true, right? I mean, it doesn't need to be true. So you see, like the subgroup property fails because you're not a binary operation under addition here. Does everyone see that? Okay. So now you see why for part A, like this notation is better because now this is a subgroup, right? So if I had a finite sum, right, plus another finite sum, like, I don't know, let's use I equals 1 to K. Oh, let's use AI prime, BI prime. Yeah. Well, this thing is still a finite sum of elements, right? It's just, how about this? It's just, how am I going to relabel this? So instead, let me label this as, I mean, it's like this is still a finite sum of things, right? I mean, it's just hard for me to index it, but this is still A1, B1 plus AN, BN plus A1 prime, B1 prime plus BK prime, AK prime, right? So in the end, like if you have a finite sum of two things, and the result is still a finite sum of two things, right? I just wrote it like this because I don't want to deal with the summation notation. So this thing is still an AB, right? So a finite sum of elements, of like A times B plus a finite sum will still give you a finite sum, right? And obviously, the 0 is in there, right? Because 0 is in A, 0 is in B, right? So I just take sum I equals 1 to 1 of 0 times 0. That so that your identity is still here, right? And then you have inverse because, well, what's the inverse? It's given by, yeah, inverse. And this thing is still in A, right? Because A is an ideal. So if AI is in A, then negative AI is in A. Because all you're doing is you're just multiplying by -1, right? And the magnet property sucks in everything you multiply by in R. So this is a subgroup, and obviously, R times this is, and again, magnet property, this is in A, this is in B, right? So this is in AB. And similarly, so here I'm using the fact A is an ideal. So now from here, I will use the fact B is an ideal, right? The other way. So it's not commutative, but it doesn't really matter because this is the ideal property. So AI, BIR. So since B is an ideal, BI times R is in B. This is an A. So this is an AB. So you see in this case, we don't even need commutativity, right? And yeah, so that's, is an ideal. And this is obvious, right? Because, and so I'll just do a quick proof, right? An arbitrary element looks like this. So this is an A because I could think of it like this, right? AI times BI, where this is an element in R. So by magnet property, this is an A. Yeah, by magnet property of the ideal A. But similarly, I could think of this as my element in R. And then this is in B by the magnet property of B. So this is in A, this is in B, right? And we proved earlier this was an ideal. So any finite sum of it, since it's an additive subgroup, will also be in. So this, every element in here is in A intersect B because it's in both A and B. And then any finite sum of it would be in A intersect B. So yeah, that's a pretty neat thing. So you think of, all it is just a bunch of ideal properties. But yeah. But the thing I want you to understand is why we don't write it like just this. Yeah, this is wrong. Do not ever do this on your final or quiz. Do not. This is incorrect. Okay, everyone clear? Yes. Okay, so I guess next time on Tuesday I will just go over. I think we're gonna move on to like fields and polynomials. I think the other TA makes it this week, but it should be whatever's gone over this week. So I guess you only had like Wednesday stuff. So